thank you very much for the introduction. So I want to talk to you about some theoretical framework we were developing over the past couple of years at the University of Geneva, mostly with Julian Tönnes and Alessio Leos in the group of Dima Abanin. So what do we actually want to study here? That is, we want to study how quantum systems behave if they are perturbed. So that extends to phenomena like thermalization, where the question is there's a given system, will it thermalize or not, or will it be localized? There are specific phases which can only be realized if the system is perturbed. Think about time crystals and the like. And it's also very crucial to quantum computing. As the previous speaker was telling you, quantum algorithms, quantum computing are essentially intrinsically out of equilibrium systems. But there's also a practical sort of engineering type problems. That is, if one looks at impurity models, for example, like phosphorescence, light-emitting diodes, and the like, or what we are going to explore, the Kondo model, which for example appears in single electron transistors. So here we are going to specifically look at the real-time evolution of local operators. So if I put a system out of equilibrium, say with a quantum quench, what happens is it will generally relax to whatever state it goes to based on well, what kind of system it is. And the advantage of looking at local observable is that they are typically measurable quantities, but they also tell you something about more global phenomena like transport properties, whether you have diffusion or ballistic, then the relaxation happens at different rates. And sometimes you have phenomena like localized modes or edge modes, depending on the system you're looking at. So those kind of observables we usually write as the expectation value of an operator at time 0, multiplied with the operator at time t, and then we average over some ensemble of density matrices. So the problem is if you want to do that in a computer because, well, maybe you cannot afford an experiment or the experiments are too noisy, then what you often do, this is one class of algorithms, is that you start with the state at time 0, and then you apply operations to it to make it to the state at time t. So in a way, this is applying U from one side to the density matrix and U dagger from the other side, in the beginning of quantum mechanics. And the problem, of course, is that for large quantum systems, we quickly run out of steam with this technique. Because, well, the Hilbert space is exponential in the number of degrees of freedom, and exponential is a very, very fast-growing function. So what one usually does is one compresses it in one way or another, and currently most popular way to do that is called the matrix product states. Which, okay, it's not very important to understand precisely how they work, but in general, they can represent low entangled states with few degrees of freedom. And so, if we want to compute this, what do? Well, we start with this initial state, then we compute and compress the state at time t, and then we just try to, well, ideally, this representation we have chosen allows us to compute observables. Matrix product states do that, so that's not a problem. But the problem with this approach is that for out-of-equilibrium systems, for many interesting problems, the entanglement entropy grows linearly, which means that the complexity, even after compression, grows still exponentially. So this approach runs into trouble very fast. So what are we trying to do about this? Well, we're borrowing an approach from the past, in this case Feynman and Vernon, because they were developing a theory, or they were looking at open systems. And what we want to do, we only are interested in local observables, right? So we don't need to like really store the entire complexity of the wave function. We only care how this complexity of the wave functions affects our local observable. And what happens quite often in the theory of open systems is that one says, okay, well, then we do Markovian dynamics, and then everything is simple. But of course, this is not an accurate description of reality, at least in many cases, there are non-Markovian effects. So what do we really have to do? Well, I showed you before this thing. This is a tensor network diagram, so if you're not familiar with it, don't worry. But in the end, this is essentially this is a computation. This is a sum. Every line means we're summing about something. And crucially, sums are commutative, so it doesn't really matter in which order we sum them. So we can do that in different order, and sometimes the intermediate states we get have lower entanglement. And that thus can be more efficiently compressed. So and what we want to do now is we want to take everything which is related to the environment and take this and treat it separately. And now, if we're just interested in this local evolution, then all that matters is what does this object, this partially contracted tensor network, looks like. Every environment which produces the same partially contracted tensor network, if we cut it like this, will produce the same dynamics on the impurity or on the local subsystem. And it also means we can replace it by a simpler environment if we find one. So in general, this idea has been around. Like in the tensor network community, people have done transversal connections, for example, Marikam Barnuls and others. In the open system community, this is called a process tensor. And like I said, it's actually a discrete version of Feynman-Vernon's influence functional, so that's why we called it influence matrix. And now, this doesn't help you much, because in a way, we just reformulated our problem. If we compute everything exactly, well, we might gain a little bit, but not much. Because of light cone effects, you can still gain a bit. But okay, so what we really need to do is we need to compress this new object. And for that, well, we can use matrix product states because we have a time direction, which is now one-dimensional. So we have, in a way, we have a one-dimensional wave function we need to study and we need to treat. And that means the criterion how well we can compress it is probably something like the temporal entanglement, the entanglement of this wave function in time. And this has a physical interpretation. It means the memory of all the information you can store in the bath, and you can also, that's crucial, retrieve in the given time window. So we set in advance, we set evolution time. And it turns out that for a lot of physically interesting systems, this has actually really low entanglement. For example, there are certain very chaotic systems where this becomes actually a product state. So you actually recover Markovian dynamics if you look at local systems. But this doesn't really depend on being an exact product state. So you can perturb from this point, which you cannot really do analytically, but you can do numerically, and you still have low entanglement, and then you can still compute dynamics there. Close to integrable points, so at integral points, like there are some analytical results where you can show that this has low entanglement, but also this applies still close to integrable points, it still will be low entanglement. And it can also treat dissipative system because it's essentially an open systems approach. And interestingly, for many body localized systems, it's not that surprising that it has low entanglement because in a way it's a shallow circuit. But you can do exact disorder averaging, which is not as useful from a numerical perspective as one might think, but it might be interesting for treating many body localization as a like symmetry breaking, in a way similar to what Sam Garrett was doing. Okay, so now I hopefully have convinced you that this is a useful object if we can compute it. So I'm now here in this talk, I will focus on the numerics. So it is also interesting to study analytically, but we actually want to compute this O of 0, O of t. So now we need to have an algorithm to actually compute this object. So so far we have developed two approaches, and one is based on just contracting the tensor network, but one needs to take a bit care to do it in an intelligent way. But for what I want to talk in this, well, today, in the next 10 minutes, will be how to solve or how to treat baths which consisting of from free fermions. Those are very interesting for for quantum chemistry applications because in a way, if you use dynamic mean field theory, which is a very popular theory to approach the Hubbard model too, like solving an impurity model, like with an interacting impurity and free fermions in the bath, is the crucial step. That's the difficult step. The rest is easy. So if we can make progress on this, that gives us advantages for in a lot of other applications. Okay, so what is the model we want to really concretely now treat? It's called a single impurity Anderson model, and just consists out of a bath part, which just has 3 fermion modes, non-interacting, very simple, and then they couple to an impurity, and this impurity has a Hubbard interaction. And well, we can define our bath either by like an Hamiltonian, like here, or we define it with what is actually quite common to do, because this is an intermediate result of DFT and DMFT, to get it as a spectral density. And then like here, okay, this is the spectral density of a chain, for example. So if you want to compute a chain, you would plug in this spectral density, which is a semicircle. And it turns out that this, even though only one tiny part of this model is interacting, this already exhibits rich physics. This is in the low energy regime, this becomes the Kondo model. And effectively what happens is that you project, so the double occupied and the empty states, they become rare because they have an energy penalty. And then what you effectively have is a spin coupled to an electronic bath. And now those electrons here want to screen this spin. So you get sort of an like a dynamic of like a dissipative spin coupling, and this is a highly correlated ground state. This is and as I said before, this is also the model you would need to solve to do DMFT, which then you can study real materials and stuff. Okay, so first I want to convince you that actually this object which I was introducing earlier, this influence matrix, has low entanglement in that case. And for that, I want to look at finite baths. So say we have a chain which is now not infinite, but short. And then we look at the entanglement, the temporal entanglement entropy, as a function of the length of our finite bath. And what we observe is really peculiar. We get a high peak, and then it becomes an area law. So why is that? Well, I told you before, the entanglement entropy is related to the information you can store in the bath and, crucially, can also retrieve. If the bath is very shallow, then you're sort of here at the slope. So you can produce those quasi-particles in the impurity. And they can travel ballistically because it's free fermions, and I said it's a free fermionic chain. But then they get reflected at the end of the chain and can come back. So if you are if you have a very shallow, like a short system size, then there are not that many opportunities for producing quasi-particles, so that they also come back. This is just related to dispersion relation. But at some point you get a lot of them, and then you are here at this peak, and that's actually volume law. So like this procedure doesn't work well for finite baths. But interestingly, if our barrier goes far away, farther than the time t, then there's no particle anymore which can reach the barrier and come back. So the only sort of entanglement you can transmit is through like sort of residual overlap with edge modes. And that means that this is a constrained quantity. There are not that many, so this becomes area law. Or in the case of a Fermi C initial state, like zero temperature initial state, it becomes a log law. So this is just as an illustration. Yes?
Do you have an idea of the threshold distance to the point at which it becomes far away for anything?
Yeah, because, okay, I was showing before this is this kind of, well, oh, maybe this is enough. This kind of tensor network, and there you have a light cone. So there's a fixed light cone which is given because you trotterize. Sorry, that I might have forgotten to mention. It's numerics, you kind of need to trotterize. So you take discrete time steps, and then like there is no way that you can get correlations outside of the light cone. It's just not possible. But also there's a physical light cone. This is like the fastest particles, so the light speed, sort of to say. You always have something like that. So this is yeah, always possible.
Quick question.
Yes.
So what entanglement are you talking about? Between the impurity and the chain, or some
No.
chain entanglement?
No. This is entanglement in time. It is entanglement of this object. So this object. it's like it's essentially you entangle the past with the future. That doesn't have any spatial component. There is no notion of space here, which makes this like quite attractive because you don't really need to care about a Hamiltonian. You can just plug in a spectral density. Okay, how do we actually compute this? This is I will just make this very quick. So you take your spectral density, you run it, you solve some Gaussian integrals exactly, and well, you need to discretize, but other than that, it's exactly. And then there is an algorithm that was developed by Matthew Fishman and Stephen White, which gives you a quantum circuit for Gaussian states. So it turns out this is a Gaussian state, and then you can compute a quantum circuit from that, which then you can contract. So if you're not familiar with that, don't worry. The only thing is there is a way to go from the spectral density to the matrix product state, which represents your influence function. So let's look at some results. I told you before that if you have a spin coupled to if you have this single impurity Anderson model and you just bring it out of equilibrium, then it's the dynamics of a spin coupled to the itinerant fermions. And well, here we see what happens if you have a quantum quench from the spin-up occupied state, and we just release it, and then it will relax to a ground state. You see that first the charge relaxation is very fast, but the spin relaxation is very slow, and that's like a crucial indicator that you're actually looking at quantum physics here, because the spin relaxation the rate is related to quantum temperature, which in this case is very low. So this is actually a plot which we did because we found a similar plot in another paper, which did this with QMC. And even though this is a method we developed and it's like very coarse, not optimized code and nothing, we were still able to really compete with the QMC results. Quantum Monte Carlo, which is a method which was developed over many years and refined to a lot, and we could compete with them on both accuracy and time scales reached. So this is pretty nice. But what we can also do is we can compute transfer problems. So we can take two baths. In this case, it would be two influence matrices, four, because you also need to account for the spin species. So you have four influence matrices in a way, and then you put different chemical potentials here and here. And then you can compute currents. And this also competes very well with what Quantum Monte Carlo do. And you don't actually need that high bond dimension, it turns out. So you can go with very low bond dimension, and you still get perfectly converged results. So yeah, what you do is you wait until you reach the steady state current. Okay. And then just briefly, what we did very recently with people from Flatiron Institute, mostly Benedict Close, was looking at imaginary time evolution, which is actually for DMFT what you don't really need a real time. Well, it's nice if you can do that because Quantum Monte Carlo sometimes has problems with that. But what you crucially absolutely need to have is imaginary time. This is much harder for some reason than real time. We don't completely understand why this is. You need really relatively high bond dimension, so this is 2 to the 12s, and then you lie on top of the QMC curves, which makes this very challenging. But the main takeaway is that in the case of Quantum Monte Carlo has problems if there are fermions, and if sometimes you can solve it, but in case of multi-orbital models, nobody really knows how to do that. So, our method would just increase the bond dimension even more, which brings us, of course, at the limit of our computational power. But in principle, there's no expectation that there should be any difficulty in extending this to multi-orbital problems. And it's also something we're working on, at least for real time right now. Okay, so a quick summary. We can compute observables by finding a compressed representation of the bath. And this can be very efficient in some even regimes where normal methods have really trouble. And we have algorithms for free fermions and what I haven't shown for one-dimensional interactive models. And this hopefully is a natural way to improve DMFT or other methods. So with that, thank you very much. And if you have questions.